Jai Hind everyone. I'm Jyoti Sharma once again in front of you, taking one of the another complex topic, which is magnetic circuit, and belongs to the subject fundamentals of electrical engineering, which is having a code of BW 101 in the AKTU first year syllabus. So while starting this topic, which is magnetic circuit, we need to in fact see what are the terms which will be related with this magnetic circuits. So first we'll be just briefing up with certain terms which are generally being involved in the magnetic circuits. So the very important term, that is the magnetic field. What do we mean with this magnetic field? So that is nothing but, whenever a magnet is there, so we feel the influence of that magnet around up to some certain surroundings, right? That can be felt through certain nails being splitted or the all pins being splitted. So they will be oriented towards the magnet. Either they'll be attracted or they will be repelled. So the region around the magnet up to which its influence that can be experienced, so that is being called as a magnetic field. Now, what do we mean by a magnetic flux, which is generally represented by phi? The total number of lines of forces in a magnetic field is called the magnetic flux. Magnetic field is experienced because we are having parallel magnetic lines of forces running from North Pole to South Pole. So those parallel lines which are having a high tension between each parallel line, these are actually the parallel lines of forces which are repelled to each other, right? And generally, when we say the magnetic lines of forces are there, it is having a unit of Weber. And when I say it is 1 Weber, it is generally 10 to the power of 8 lines of forces present, approximately. Right? So 1 Weber is almost equals to 10 to the power of 8 lines of magnetic forces. Similarly, what do we mean by magnetic flux density? Flux density. So that is the magnetic flux passing through a unit cross section. Then it is being called as a magnetic flux density. Generally, it is represented by the letter B, as it is nothing but flux per unit area, flux flowing through a cross section area. If that is so, the flux is having a unit of Weber. We have just seen area, it is per meter square. So it is Weber per meter square, and it is also being called as Tesla. Now, magnetic field intensity, it is also being called as magnetizing force, or it is also being called as magnetic field strength, right? So it gives the measure of the strongness or the weakness of a magnetic field, right? It is actually the force experienced by a unit north pole, present at a particular instant at a point in a magnetic field. So this magnetomotive force, which is nothing but MMF, this is the driving force we'll be studying, driving force behind the production of the flux. If this magnetomotive force, when it is acting per unit length, then it is being called as the magnetic field intensity. H is the representation for the magnetic field strength or magnetic field intensity given by F upon L, where this F is what we are calling it as MMF, also given by N into I. Right? N into I. Obviously, this magnetic field intensity, it is because of the number of turns and the current which is flowing in the exciting coil, that is given by the MMF, number of turns multiplied by current. Because we need to have, to establish a flux, we need to have an exciting circuit. This exciting circuit is having certain number of turns and a current flowing through it, right? This N into I gives me the MMF, the magnetomotive force. It is the force behind the production of the flux. And when it is divided with the active length of the conductor, the active length of the magnetic circuit, right? That will give me, or the mean length of the magnetic circuit, that will get me H, Ni by L. What should be its unit? Ni by L. Number of turns, current, ampere turn per meter. So its unit is ampere turns per meter. And we do have a relationship between this H and this B. H, we have just seen magnetic field intensity. B, magnetic flux density. They are related by the equation B is equals to mu H, where what is mu? Mu is nothing but the permeability of a particular material. Now, we'll be seeing what the permeability is. First, going with magnetomotive force, MMF. We just discussed it is the driving force to drive a magnetic flux through a magnetic material, and that can be given by the product of the number of turns and the current flowing through that exciting coil. Obviously, its unit has to be ampere turn, or it may be just given by just amperes, because turns is just the number of turns which used to be there in the exciting coil. Now, permeability. What is this permeability? It is actually, if at all I see, the permeability is the property of the material, right, by the virtue of which it provides the ease of making the flux to flow through a given medium, right? It is the ease by which a material can make a flux to flow through it. A medium can make a flux to flow through it, right? So the permeability, the magnetic conductivity of an iron as compared to that of an air, right? Not only an iron, but it can be any medium. Medium can be generally, because we are talking this in terms of the core material, which is generally a ferromagnetic material made up of iron and the alloys of iron. So when it is compared with the air, it is being called as permeability. It is of three types. One is absolute permeability, mu. Another one, permeability in free space, that is mu naught. And the third one, relative permeability, which is mu r. So what is this absolute permeability? So the absolute permeability, it is nothing but the ratio of the magnetic flux density in a particular medium to the magnetizing force or the magnetic field strength producing that magnetic flux density in that particular medium, other than free space, vacuum, right? So this is given by the absolute permeability. Now next one, mu naught. This is nothing but the permeability in free space, which is going to remain constant. It is once again the ratio of B by H, but in free space, which is going to remain constant at any place in a vacuum, which is given by a constant, which is being called as 4 pi into 10 to the power of minus 7 Henry per meter. That is, unit is Henry per meter. The third one is relative permeability. Relative permeability, it is the relative permeability of a medium is given by the ratio of the flux density in a given medium by the flux density in a given medium by flux density in compared to free space, right? Having what is the same? Having the same flux, having the same magnetic field intensity. So if at all I go with the ratios B by B naught, once again, B is equals to mu H and B naught is equals to mu naught H, but H is same. So once again, the ratio is mu upon mu naught. So the relationship what I get with mu and mu naught, so I'll be getting mu is equals to mu naught mu R. That means the absolute permeability is equals to the product of the permeability in free space multiplied by the relative permeability. Once again, what is the unit of absolute permeability? It is Henry per meter, because mu naught is having a unit of Henry per meter, but mu R, it is relative, B by B naught. It is not, it is a unitless quantity. So we get the permeability, absolute permeability, as Henry per meter as its unit. A very important property of a magnetic circuit, which is reluctance. So what is reluctance? Likewise, we used to have resistance in an electrical circuit, which gives the opposition to the flow of current. Similarly, here, reluctance is the resistance or the opposition offered by the magnetic circuit to the flow of flux, right? If we just see, we'll be comparing also. A magnetic circuit is very much analogous to an electrical circuit. Many of the quantities are very much analogous, right? So the quantity which is analogous in electrical and magnetic circuit, like was reluctance. In case of electrical circuit, we used to have resistance, right? So once again, likewise, the resistance, which depends upon, if at all I go with resistance in an electrical circuit, that is given by R is equals to rho L by A, where rho is the resistivity, length is the active length of the conductor, A the cross-sectional area. Likewise, in case of magnetic circuit, S can be given as L upon mu A, where once again, this L is the active length of the magnetic circuit. Mu is, which we have just seen, it is the permeability of the magnetic material, which is given by mu naught mu r again, and A the cross-section area, right? So it depends upon three things: length of the material, cross-section area of the material, and the permeability of the material. So if we see what is the Ohm's law being referred in electrical circuit and in a magnetic circuit. So if at all I see Ohm's law in electrical circuit, an electromotive force is there, a resistance is there, and a current is there. V, I, R. Similarly, when it comes to a magnetic circuit, it's a magnetic circuit. I'm having a magnetic core. Air gap may be present, may not be present. I'm having an exciting coil, which is having certain source being given, certain currents being given with certain number of turns. So if at all I'm having certain number of turns in current, then obviously I'm having the magnetomotive force F given by number of turns into current. F is given by N into I. So when the magnetomotive force is there, that is the force for the production of the flux. So depending upon the current direction, the flux will flow. So another quantity is flux, right? Then obviously this magnetic circuit is going to oppose the flow of this flux through it. Likewise, the resistance, which we call it as reluctance, represented by the letter S. The unit for this reluctance, we have just seen, S is L upon mu A. We'll be, in fact, deriving its unit from here, from the law. This is S is L upon mu naught A. Flux, that is the magnetic lines, total magnetic lines of forces flowing through it, right? So in case of electrical circuit, we used to give it as V is equals to IR. So the electromotive force is equals to current multiplied by electrical resistance. Similarly, in a magnetic circuit, now the magnetomotive force that is given by F, that must be equals to flux multiplied by reluctance. Magnetic flux multiplied by the reluctance. If that is so, from this particular case, I may derive reluctance as, it can once again be given as F upon flux. F, the magnetomotive force, having the unit of ampere turn. Flux is having the unit of Weber. That's why the reluctance is having the unit of ampere turn per Weber. One of the important property, that is permeance. What is permeance? That is just the reciprocal of the reluctance. Likewise, in electrical circuit, the reciprocal of resistance is conductance. Similarly, the analogous term for the conductance in case of magnetic circuit is permeance. It gives the reciprocal of the reluctance 1 upon S. So the unit will also be reversed, Weber per ampere turn. Going with a comparison between the electrical and the magnetic circuit. So if at all we see the comparisons, the very first one is the path traced by the circuit is known as the electrical current, but the path traced by the current or the flow of the electrons, that is known as the electrical circuit, whereas the magnetic circuit, the path traced by the magnetic flux, that is being called as the magnetic circuit. If at all I say, what is the driving force in the electrical, second point, the driving force in the electrical circuit used to be EMF and its unit used to be volts. Whereas in case of magnetic circuit, the driving force used to be MMF and its unit used to be ampere turns, right? There is a current I in the electrical circuit which is measured in ampere, whereas the analogous term for the current in case of the magnetic circuit is we used to have flux and its unit is in Weber. In case of electrical, the flow of the electrons decides the current in the conductor. The flow of the electrons decides the current. Whereas in case of reluctance, in case of electrical circuit, the number of magnetic lines of forces that decides the flux. Similarly, in case of electrical circuit, the resistance that opposes the flow of the current and its unit is ohms. Whereas in case of magnetic circuit, we used to have the opposition offered to the flow of the flux that is being called as reluctance, denoted by the letter S, having a unit of ampere turn per Weber. The resistance that is given by rho L by A, directly proportional to L, inversely proportional to A, and depends upon the nature of the material. Similarly, the reluctance is given upon 1 upon mu naught mu Ra or just mu A, which is directly proportional to I and inversely proportional to the permeability, right? The law, the current is given by EMF upon resistance in case of electrical circuit, whereas in case of magnetic circuit, the flux can be given as MMF upon reluctance. Likewise, in case of electrical circuit, we used to have current density, J, current per unit area, right? Here, we used to have flux density given by B, given by flux per unit area, Weber per meter square or Tesla. We used to have two basic analysis laws, Kirchhoff's current law and Kirchhoff's voltage law, that is being applicable to the electrical circuit. Whereas in case of magnetic circuit, current is analogous to flux. So we used to have Kirchhoff's flux law. Similarly, voltage law, the analogous to voltage is MMF. So we used to have Kirchhoff's MMF law and flux law, which are applicable to the magnetic circuit. Certain dissimilarities, if at all I say. So in the electrical circuit, the current actually flows and there used to be a movement of electrons, right? But in magnetic circuit, due to the MMF, the flux get established and it does not flow in that sense, or as we used to say for in case of current, right? The another one, if it all we say, there are many materials which can be acting as insulators in case of electrical circuit, right? Through which the current can't pass through. Likewise, air, PVC, synthetic resins, right? So, which cannot have the current to be flowing through them. Whereas, if at all we just see in case of magnetic circuit, there is no perfect magnetic insulator. So, the flux can pass through all the materials and it can even pass through the air as well. That's why we used to have small air gaps, right? The third point can be the energy in case of electrical circuit that must be supplied, that must be given to the electrical circuit to maintain the flow of the current. As you remove the supply, the current will not be there, right? It will stop working. Whereas in case of magnetic circuit, the energy is required only to establish the flux, right? But it is not required to maintain it, right? It will be maintained, though with a reduced value or whatever, but it will be there. The flux is required only to maintain it, only to establish it. Then another point which creates a dissimilarity is the resistance and the conductivity are independent of the current density under the constant temperature, but they may change due to the temperature, right? Whereas in case of magnetic circuit, the reluctance, the permeance and the permeability are dependent on the flux density, right? The last point which can be given is the electrical lines of the fluxes, they are not closed. They start from positive charge and end on the negative charge, right? Whereas the magnetic lines of fluxes, these are closed lines. They flow from the North Pole to South Pole externally, while South Pole to North Pole internally. So they are closed. So these are certain points of comparison between electrical and magnetic circuit. Now we need to in fact understand the magnetic circuit to solve them, right? So a magnetic circuit, if at all I say, it can be just given by the simple structure, a simple magnetic circuit, right? Say it is a simple magnetic core having certain number of turns, having certain exciting current being given I. then definitely this N into I will get me the MMF, the required MMF for the production of the flux, right? If it is having a mean core length of LC, cross-section area of A, magnetic core permeability is same mu. How can I represent the same magnetic circuit with its electrical equivalent? So I'm having an MMF. The MMF would be having, that means a source. I may be representing it with with a voltage source, EMF, a DC voltage source. The reluctance of this magnetic path can be represented by the resistance, and the flux can be represented by current. So it's a simple series circuit. It's a simple circuit having a voltage source, a resistance, and a current being shown. Say if a magnetic circuit is having an air gap, right? I'm having an air gap over here. The same circuit. In the core, I'm having an air gap. Now, how this would be represented? It is having an air gap length. The area is AG. It is having certain air gap length also, say LG. The air gap length is G. So, how can we now represent its electrical equivalent? Once again, source is only one. So, I'll be having a single EMF source being shown. So, that we are representing over here. Then, this is the equivalent magnetic circuit, what it can be seen. The electrical circuit can be drawn. This is magnetic circuit. This is N into I. This is the magnetomotive force being produced. A single magnetomotive force having a common flux. But how many reluctances? One is the reluctance offered by the magnetic path, and one is the reluctance offered by the air gap. So I'm having two reluctances. One is by the air gap and another reluctance is with the core material, right? But both of these are experiencing same flux. So this is an example of a simple series circuit. If at all I want to have its electrical equivalent. So I'm having a source. Then how many resistances? Two resistances. R1 and R2. R1 is representing the reluctance for the iron path and R2 is representing the reluctance for the air gap. The current is flowing I and I'm having an voltage source E. So this is the electrical equivalent. Similarly, what we were just discussing, that the magnetic circuit can be subdivided into two, series magnetic circuit and parallel. We have just seen the series one, right? Having this one is the circular ring, having an air gap. It can be represented with a single voltage source and the two resistances in series with a common current. A parallel magnetic circuit instead is having now three limbs, right? And on the central limb, the source is being wound. I mean, the MMF would be created in the central limb as the source is here. Say this is the total flux phi. Now, at this point, the total flux would be divided into two. Phi 1 and phi 2. One would be phi 1, one would be phi 2. Depending upon the active length, depending upon the cross-section area, and depending upon the reluctance, obviously, depending upon the reluctance, these property decides the reluctance of this path and this path. If all the properties are same, the length is same, the permeability is same, the area is same, if that is so, this flux would be divided equally. But if these parameters are different, the length is different or the area is different or the permeability, the material, a different material has been used over here whose permeability is different, then definitely I'll be having a variation in the fluxes. But it will be divided into two, phi 1 and phi 2. Right? So how can I have its electrical equivalent? Now the source is at center. So the EMF is at center. How many reluctances would be shown? One, this is the main current, right? This is the main current being shown. Then this will be dividing into two parts, I1 and I2. I1, this part of the magnetic circuit would be giving me a reluctance and the equivalent, electrical equivalent of that is being represented by Ri. Similarly, this path, say let's name it. The name of this can be given, say A, B, C, D, E and F. So for the path A, B, C, D, for this path, the reluctance offered and its electrical equivalent is given by Ri. The reluctance offered for the path AFED and its electrical equivalent is given by the resistance, once again Ri. Which path is remaining? The center path. It will also offer the reluctance. But don't forget, I'm having an air gap also over here. LG, I'm having an air gap. So here the center path will show me two reluctances or two equivalent resistances. One for the central limb reluctance, I'm calling it as RG. And one for the air gap, I'm calling it as Ri. That will be shown in the center limb. I know that this I has to be the addition of I1 and I2. All the three are in parallel. So this net voltage, this voltage is going to remain same. Similarly, I can be saying it for the MMFs. That means the MMF for AD must be same as the MMF for ABCD, and that must be same as for AFED. Right? So this is the analysis of series and parallel magnetic circuit. Going with the numerical. Before that, just seeing a series magnetic circuit, it's in fact a composite magnetic circuit, right? Having three different materials being used. It's a circular ring, right? If it's a circular ring, having three different materials, having three different areas, having three different lengths. To here, up to here, to here, say it is iron, right? The material is iron. It is having a length of L1, having an area of A1, and obviously having a permeability of say mu I. Another material which is connected in series with it, it's a composite material, say that is cast steel, right? It is having a length of L2. This is having a length of L2, area of A2. Third material, some other material, cast iron or alloys of iron, that is being used. It is having a length of L3, having an area of A3. But the flux, if at all we say, that is going to remain same. It's a series magnetic circuit. Right? How can I represent it? It's with an electrical equivalent. The source is single. I'm having a single source of MMF. That means I'll be having a single battery. Right? But how many reluctances? No air gap. So I'm having now three reluctances equivalent R1, R2, R3. That will be shown by three resistances, right? This is the induced EMF, E. The current flowing would be same with three resistances, where R1 represents the reluctance for this path. That means for first material. R2 represents the reluctance for second material, and the R3 represents the reluctance for the third material. This is a series magnetic circuit. Taking an example for a circular ring, iron ring of mean diameter 25 centimeter and a cross-section area 9 centimeter square is wound with a coil of 100 turns and carries a current of 1.5 amperes. The relative permeability of the iron is 2000. Calculate the amount of flux produced in the ring. How much is the flux produced in the ring? Right? Everything which has been given is also shown in the figure as well, which is there. It is a circular ring having a current of 1.5, this exciting coil. It is having the number of turns of 100. The mean diameter has been shown as 25. The area is 9 centimeters square. So the mean length of the flux path, that is given by pi d. So pi d centimeter, I'll be converting that into meters. So it is 0.785. Then the flux is given by our MMF law, Kirchhoff's Ohm's law, that the flux is given by MMF upon reluctance. MMF N into I. The number of turns is also known, that is 100. Number of turns is 100, current is 1.5. Substituting that, divided by reluctance. The reluctance is given by L upon mu naught mu R A. It's a simple circuit. It is not having any air gap right now. Right? It's a simple circuit. If at all I want to draw its electrical equivalent, it's just a voltage source, a single resistance, and the current being flowing. This is E, this is R. What I'm asking, the quantity which is being asked is flux, right? And here I want to have current. So that will be given by E upon R. Similarly, here the flux would be given by mmf upon reluctance. If that is so, reluctance L upon mu naught mu R A, 0.785 is the length. Then reluctance mu naught, 4.10 to the power of minus 7, mu R, relative permeability, it's already being given as 2000 multiplied by area. The area is 9 centimeters square. Converting that into meters, 9 to the power of minus 4. So we'll be getting the flux as 0.431 milliweber. Taking another example, a rectangular shaped iron core has an air gap of 0.01 centimeter. The mean length of the flux path through the iron is 39.39. The relative permeability of the iron is 2000. The coil has 1000 turns. The cross-section of area of the core is 9 centimeters square. Calculate the current required to produce a flux of 1 milliweber in the core. So the flux this time is already being given and we need to calculate the current through which will produce this flux. So obviously if we require the current, what's the relation? I need to have mmf, number of turns multiplied by current, that will give me mmf. If this mmf is known, I'll divide it with the number of turns so that I can be having the current flowing through that exciting coil. To have that, once again, mmf is given by flux multiplied by total reluctance. Now, why this total reluctance? Because this is a series circuit. It's a rectangular core, but it also have this air gap. So I'll be having now two reluctances. This total reluctance is given by the reluctance of the core part plus the reluctance of the air gap. S is equals to SI plus SG. So S is given by, once again, length of the iron path and its permeability and area, length of air gap, permeability and area. Substituting the values, the length of the air gap in meters, 39.09, 10 to the power of minus 2. This is mu naught, mu r, 2000, area, 9, 10 to the power of minus 4. Similarly, length of the air gap, it's 0.01 millimeter, 0.01, the length of the air gap is being given as 0.01 centimeter. So converting that into meters, so 0.01, 10 to the power of minus 2. Once again, this is mu naught A because in case of air gap, the mu r, relative permeability, is 1. So this becomes this. Substituting the value, once again, we'll be getting the reluctance as 295.45 10 to the power of 5 divided by 36 pi. So flux, we have just derived, that will be given by mmf upon reluctance. mmf, number of turns into I, 1000 into I upon total reluctance. Substituting the value, we'll be getting the current as 0.26 amperes. The last numerical, which is a numerical on parallel magnetic circuit. A magnetic circuit, it is having its winding on the central limb. The cross-section area of the central limb is 10 centimeters square, where the cross-section area of the outer two limbs is 5 centimeter square. And for the center, it is 10 centimeters square. The effective length of the central limb is 16 centimeter. And that of the two outer limbs is 25 centimeter for this outer. Both the outer are having 25 centimeter. Calculate the current required to flow through the windings, which has 1000 turns. This winding is having 1000 turns to produce a flux of 1.2 milliweber in the central limb. That means the total flux is going to be 1.2 milliweber. Assume that for a flux density of 1.2 Weber per meter square, the magnetizing force is 750 ampere turn per meter. So draw the equivalent electrical circuit. So we can draw the electrical equivalent circuit, right? The source would be at the center. Then the reluctance for the center path, RC. The reluctance for the right hand side limb, R0. The reluctance for the left hand side limb, R0. Why both are being written as R0? Because all the parameters are same. The length is same, the mu r is same, the cross-section area is same. So, it is having same reluctance. So, the fluxes are going to divide equally. right? So the total current, if at all it is I, electrical equivalent, then the current is going to divide as I by 2 and I by 2. If that is so, now the flux density in the central limb. How can we have the flux density in the central limb? Flux upon area. So what is the total flux in the central limb? 1.2 milliweber. Area is 10 into 10 to the power of minus 4. So we are getting the flux density as 1.2 Weber per meter square. Similarly, the flux density in the outer limb, which will be same as that for the central limb, since half of the flux is available in each of the outer two limbs, their cross section area is half of that of the central limb, right? So we'll be having B naught is equals to phi naught upon A naught. Now in this case, phi naught is half. This flux would be divided into 2. 1.2 into 10 to the power of minus 3 is going to get divided into 2. So it is 0.6 milliweber, right? Divided by the area, that is also again half, which has been given in fact, given by 1.2 Weber per meter square. So here also the flux density is 1.2 Weber per meter square. Now the corresponding H, that means magnetizing field, the field intensity or the field strength for 1.2 Weber per meter square, that has been given as 750. So the total MMF required, what will be the total MMF required? If at all I say, what is the net voltage? So the net voltage required, this must be equals to either this path or this path, right? So I may be saying the voltage for this path plus the voltage for this path, or either the center path plus this another one, right? I may be applying my KVL either in this of the mesh or in this of the mesh, because both the voltages, as both of these are parallel, both the voltages are going to remain same. So what is the net MMF? So that is going to be the total MMF required is equals to the MMF required for the central path plus MMF required for one of the outer limb, any one, which is going to remain same for both. So H can be given as now MMF upon L, that is MMF can be given as H into L. The total MMF required is H for 1.2 Weber per meter square, that was 750, into L, that is converting that into meters, we are having 16 above 100. Similarly, that is 750 into 25 upon 100. So we are getting that 307.5. So the ampere turns required or the MMF required, that becomes 307.5 ampere turn. How many number of turns are there? 1000. So the current required for establishing that much amount of flux becomes 307.5 upon 1000. That gets me 0.3075 amperes. So this is done from my side for the series and parallel magnetic circuit. Hope you have understood it.